Hello and welcome to the FlowCAD webinar. My name is Petra and my colleague Dirk is here with me today. Let me briefly introduce our speaker. Dirk studied electrical engineering with a focus on communications engineering and has in-depth knowledge of various software products from the EDA environment that cover signal and power integrity as well as thermal-aware electronics applications. You will now receive a brief overview of the Sigrity X tools that can be used with two tokens. By selecting examples, you will see which typical analysis tasks you can perform on your design at different times. But first, we will take a look at the Sigrity X token license model. With that, I'll hand over to Dirk.
Thanks, Petra, for the nice introduction and a very warm welcome also from my side. These two graphics are intended to give you an overview over the tools and applications available. On the left side, you will see the tools you can use to get started with the simulation. As a cockpit, you can, for example, start with the Sigrity Aurora in-design analysis and then perform subsequent more in-depth analysis. The analysis on the speed EM on the right-hand side are then aimed more at experts level. So get ready to discover the versatility available to you with the Sigrity X token licensing model. So the Sigrity X token license model is designed to provide a flexible, on-demand access to its broad portfolio of signal integrity and power integrity, as well as thermal and electromagnetic simulation tools. So tokens represent units of usage. Instead of assigning, say, one user license of tool A and one user license of tool B, you purchase a tool of tokens. A user, when launching a simulation, consumes one or even more tokens corresponding to the tool or the checked-out engine, the simulation engine they use. So different tools may consume different token counts or durations. In this webinar, however, I will limit myself to the use of two tokens. After the license is no longer in use or has been released, the tokens return to the pool and can be used for another tool or user. This tool-based model means you don't need to map each user to each tool individually in advance. It gives more flexibility. So in short words, the token license model for Sigrity X is about flexibility, efficiency, and scalability. It enables design organizations to use a wide range of simulation tools without being locked into rigid per tools licenses, and to scale simulation access up or down as project demands shift. So starting here, as mentioned before, with the Sigrity Aurora environment, or even with also called here the in-design analysis. If you already have the OrCAD X Professional or Allegro X Designer, you have the impedance and coupling scan directly on hand without any additional license. You just need to install the Sigrity X toolkit. The furthermore analysis workflows are then required by the Sigrity X Aurora license or even with the two tokens. I will dive into the workflows a little bit later on. Yes, so since we had a very deep webinar about the Aurora usage, you can get the download link or the presentation upon request. So because in this, I want to keep the introduction quite short. So let's start with a signal integrity analysis that can be done with the in-design analysis. Typically, as you know, you have to achieve a quite smooth impedance profile on your PCBs to minimize signal reflections or other bad things. With the in-design analysis, you can directly see where you maybe have some impedance discontinuities that can cause here such ringings, reflections, and other things. Due to the still decreasing size of your components and PCBs, you need to route your signal traces more and more closely to each other. That could even create a lot of coupling issues and crosstalk issues. That is also something that you can achieve, that you can analyze with the InDesign analysis. So let's get started and see how that works. In the PCB designer environment, here I shown the Aurora environment, PCB designer environment. You just select a couple of signal nets of interest, and then you can directly run the impedance scanning. As a result, you get a colored overlay with a slider here on the right-hand side. If you move the slider, you can use it as a filter, so that only the main hotspots, let's say it as a hotspot. That means all those impedances that are far away from your nominal impedance are then shown. That makes it easy to analyze and to find such areas where you have a big impact of your impedance mismatch. It's also very nice to have is the table that can be sorted like an Excel table. And here we have the most weak impedances here on top. And once you double click on one of these trace segments, the cursor automatically jumps into the design, and that makes it easy to find those areas of interest and to change it. Here in this case, for example, the signal has been routed over a split where we do not have a direct reference plane under the signal, and that makes it, or that creates the huge impedance impact here in this case. And you do not need to change your PCB editor. You just pick up the trace here, move it over the solid reference plane, and then you are done. Maybe you can rerun your simulation again. See, oh no, in this case, I've fixed this issue. And that is one of the most important things, that you can do all this InDesign analysis here directly in the PCB editors. If you want to follow up with some more deeper analysis, like to see the real waveforms of those affected signals, you can use the reflection workflow. In this case, you have to assign IBIS drivers, transceivers for the driver and receiving side, so that you get realistic waveforms. The tool provides 3 different types of general or the default IBIS models that cover technologies like 1.2, 2.5, and 3.3 voltage technologies, and where you can also adjust the rise and fall times by some special values. And this gives you, if you run the simulation right now for some selected nets, that gives you all now the waveforms over about your design. And then you can analyze whether the ringing, the reflections, or whatever else still meet your requirements, or if you need to adjust some parameters or even to move some traces away. So if you have vendor-specific IBIS models on hand, you can attach them to the analysis, of course, as well. So as we have seen here now, the signal has been routed over the split. We all know about, or have heard about, the rules that you should never route signal traces over split in planes. Why is it? Because the return path, the current return path typically runs directly below the traces. And if there's a gap below the traces, the current return path must search away through your complete design to close the loop. And this could affect a lot of bad effects, like picking up a lot of noise when the current return path goes through an unpredicted way through your design, or it even can also cause EMI issues. We have, for example, here this return path workflow that visualizes the return path on your design. As we can see here on the bottom side, the return path is directly below our traces, and that is, of course, the best results that we can achieve. But once we route here this signal over the split, we see, okay, here we have the return path directly below our signal. But here in this case, of course, the return path must search away somewhere in the design. And then when we toggle through the complete PCB on different layers, we can see, for example, here on layer 3, that was on layer 5 here, that the complete shape here is marked as red. This spreaded value or image represents that there's no direct way for the return path to close the return path loop. And if you go to another way, to a layer, for example, to layer 2, where it's the ground plane, you also see that the return path also runs over this area. And as a conclusion, you can say, okay, hey, the return path goes to somewhere unpredictable through my complete design, and that can cause a lot of EMI issues, noise, radiation, and so on. Therefore, it should be avoided in this case. So let's switch over to this power integrity analysis. Here we have the DC and AC analysis, and also we may also add here the thermal analysis that are available. For DC analysis, we have we focus here on the voltage drop of the power planes that are caused here by Ohm's law. That means we create a current runs through the power distribution network, and because of the resistive losses, we get some voltage drops. And we must make sure that the voltage is at the receiver side, or its receiver ICs still meet the voltage requirements. Furthermore, we also have to achieve a stable power distribution network without any resonances, where also all these decoupling capacitors have to be analyzed. And that is now can be done with the AC analysis that I will show you later on. And finally, we also have the possibility to do some minor or first order thermal analysis, as shown here, that I will also present a little bit later on. So let's start here with a DC analysis, meaning the DC IR drop analysis. To do this, we need to define the VRM, the voltage regulator, as the source, and the sinks where we need to know how much current goes into the sinks. That's all that for the setup. If we have quite complicated power distribution networks, as it is usually the case, we can use the power tree. This is a very nice additional tool or even feature that enables you to characterize very complex power distribution networks. That also includes all those discrete serial elements like filter structures like capacitors, inductors, shunt resistors, transistors, or even more things. So in this case, you can configure them, or you can model them, these discrete elements, so that finally you will create a complete closed current loop from the voltage regulator to your sinks, or even to your loads. So it's very nice to work with the power tree. As a result, you can see here the voltage overlay, and also we get table form. And I think it's also very interesting to see here the current distribution, which shows you how the current flows from the sources to the sinks. And especially here in this case, we have a lot of these via arrays, and that helps to analyze and to understand how the current goes through all these vias, and if there's a smooth transition over distribution of the current through your complete design. Now I want to switch over to a simple or a nice example that can be run, as mentioned before, directly in your PCB editor. Here we have assigned the voltage regulator, which is located here at the left-hand side, and over the complete design, we have a couple of different loads. And here in this case, you can see, here at the top, we have a very small and narrow shape where all this current has to go through. If you analyze such a design on a for ice principle, you may see, okay, hey, this could be a bottleneck, but I'm pretty sure that you would not see that there are some additional vias here that narrows the path additionally. And here, that makes it quite simple to see here with using the current density that shows here that we have a very, very small path where the whole current has to go through. And this also impacts temperature increase. we cannot do this temperature analysis with the InDesign analysis. We need to switch over to a power DC values thermal solver, for example, but that is not available with these two tokens. Therefore, I have to skip it. But on the other hand, if you can avoid such narrow areas here, then you can also make sure that you can avoid such temperature effects here in these cases, and then you are fine. And such high currents and temperature differences may also occur thermal stress at these areas, and also can create a lot of or decrease the reliability of your PCBs. So once you fix these problems, directly do it here in your design, enlarge the shapes, and then rerun the simulation. The simulation for this IR drop analysis takes less than half a minute, and then you can see, oh, I already achieved a very, very good result here just by enlarging the shape a little bit wider, and then we can see that was a good idea. On the other side here, that is the output of our voltage regulator. We can see here this output pin. The whole current goes over this inductor. Direct only uses one via here in this case. That means this one via has to carry the complete current for this of this power distribution network. And then you can say, oh, that also might be overloaded. That is shown here in the table below. That automatically calculates the current distribution in all those vias. And from this, you can say, okay, what happens if I add some more additional vias? You just do it also here in the layout. Just copy and paste some vias here around and rerun the simulation, get a new idea about the current that goes into your design, through your vias. But you also can see, oh, in this case, yes, now we have a better distribution, more smoother distribution, but this via below, in principle, does not carry any current. So if it doesn't carry any current, we can remove it to save some areas again, and maybe we can place it somewhere else to get a very nice, smooth current distribution. This kind of optimization is very often used, for example, from our automotive customers, to optimize such via arrays, as we have seen 2 slides before. So this is one of a very, very nice example, and hope that helps to ensure a better reliability of your design. As next, as I've mentioned, we want to see how we can analyze AC effects here on our board. That means we have to make sure that the placing of the decoupling capacitors is made pretty well. To do this, we have it's called here power inductance workflow, which calculates the loop inductance from your power pins of your capacitors to your voltage distribution network. Here at the top, you can see the connection line from the capacitor, from the top capacitors that goes to the second, and then it goes down into the PDN power distribution network in the inner layers. So this is also very long. Since this is a very long trace, we even get a very high inductance in this case, and we can see this in the table as shown here below. So it is now a very nice way to double-click here on such a capacitor. The tool automatically jumps into the design again, shows where the capacitor is located, and then you can see, oh, yes, I understand we have a very long, or not so optimal connection from my capacitor pins to the power distribution network. Let's shift it, move it away, optimize the connection, reduce the trace length, and rerun our simulation. Then you will be sure that I will be sure that you can achieve a better result that even goes into the direction of the rest of these capacitors. And then that makes it, as a result, you have now a better performance of your decoupling capacitors at this moment. So that is the main cause or main root, the reason to do this And I think it's also very, very simple to do it in the layout without going having very deep background knowledge about the theory, what to do in this case. So just follow the tool here and optimize your design. Finally, we also have this temperature or this thermal workflow. That is, I think, from my point of view, very useful in the early design stage when you perform some placing studies. To do this thermal analysis, you need to assign power dissipation value to your components of interest, as shown here. And then you say, okay, I rerun the simulation. That is a so-called thermal-only simulation where you do not need, where your design must not be completely electrically finished. So you can do it at a very, very early design stage, and also to do some what-if analysis in terms of, for example, checking different copper thicknesses for your power distribution networks. It might be a very good way to check if it might be possible to use a half-odds copper, 1-odds or 2-odds copper of your PDN layers, and to see if the temperature will be spread widely enough from top to bottom side and spread out the temperature of your design. And sometimes it makes sense to use thicker copper thickness instead of using additional cooling equipment like heat sinks or whatever else to your components. So this can be done very early, as mentioned before, in the design process, and helps, for example, to save some money with additional cost of your design. So, okay, I think that was a very brief overview of these Aurora tools. Now I want to switch over to SpeedEM. It is quite a different tool because here we have a so-called FDTD solver. That means we have a finite difference time domain solver, which is which is doing some transient analysis. So it's quite a little bit different to the other analysis. So with SpeedEM, for example, you can calculate accurate results of the PCB impedance profiles and also take care of the coupling issues. I want to skip this because the results are quite similar to those as we have already seen with Aurora. But the beauty of the SpeedEM tool is that you also can do a lot of transient analysis in terms of power ground noise distribution, near and far field radiation, EMI radiation, and some other interesting tools or analysis like ESD and TDR analysis, which I want to show you in the next few minutes. At first, I want to start here with the SRC-SI matrices, which means SRC means that we have a simulation rule check that is quite a little bit different to ERC, and that means electrical rule check. So with the simulation rule check, that is intended to evaluate the key signal integrity parameters of high-speed channels, so such serial links or source synchronous buses. So here we do not have to extract the traces in the frequency domain. We do all this analysis in the time domain, which enables us to simulate very large groups of nets. There are 3 levels available of complexity that I want to show you in the next slide, where the differences are, and in principle how the simulation works at all. Since I've just mentioned that we are using here a time domain solver, we need a transient excitation of this of the boards of the devices. The devices itself here, for example, I'm choosing here the complete memory bus, are now separated into the typical memory groups like address, command, data, strobe, and clock groups. That is assigned here in this case, for example. Afterwards, now we have to assign here the data pattern for the drivers that has to be done here. That is so typical like, yes, this is like a PVL as we know it from a SPICE notation, for example. On the receiver side, you can change the on-die termination if their parameters are available. So once you run this analysis, we get now the 3 different results here based on the 3 levels. On the first level, as shown in the slide before, this is based on an ideal power distribution network, but it includes the transmission line losses, delay, and reflection effects. In the middle, we also use the ideal power distribution network, but also via crosstalk effects are included in the simulation, and we see this as a far end and near end and far end crosstalk representation here of the orange and blue lines. And the final on the right hand side here, that this analysis of the level 3 also does not is not based on the ideal power distribution network, but it is now running on a non-ideal power distribution network that also includes some simultaneous switching noise effects, which now also can be shown here especially in the crosstalk effects here, as we can see here, and also we see that also the transmitted and received signals also get some more noise into the design. So in principle, this simulation check, or SI matrices check, results as an obtained using the layout-based time domain transient simulation. And that gives you a brief and fast overview of those signal integrity performance matrices based on the received signals, and of course here in additional here with the crosstalk factors, crosstalk signals. To perform more detailed analysis, we have this so-called EM-aware SI simulation workflow. So this simulation mode explicitly accounts for non-ideal power ground effects. So instead of assuming, as we've seen before, the ideal power ground planes, this workflow considers the real layout of the power distribution network, including coupling, plane resonances, power ground noise, and also the decoupling capacitors. So that is this power-aware aspect here of this setup. With this simulation, you simulate directly on the layout using also this FDDT engine, and which avoids here some of the errors of approximation introduced by when you reduce some models. So and since we have all effects included in our simulation, we get a very high accurate results that also includes the ground bounds, power supply noise, and simultaneous switching noise effects, all in this setup. To do the setup here is similar to the SRC matrices setup, but we also have to configure the voltage distribution network in more detail. For example, here we can see that we have this voltage regulator, which is also defined by a special SPICE model. Additionally, all these controller models are assigned by effective IBIS models. These IBIS models must be power-aware capable. So you cannot use simple IBIS models like version 3 or whatever else. So you need to have these power-aware IBIS models that directly really enables these power distribution network proper effects here, with also in accordance with this IBIS models. Yeah, in principle, that's here, and here you can see that we all have to assign these power and ground pins associated with our design, and so that we can finally get a very, very detailed simulation setup for our analysis. As a result, we can also get here for a complete bus, for this memory bus, the results. This is the result of the complete bus. which took about a significant the calculation on my notebook took significantly longer than it was in comparison to the SRC matrices. So to run this EM-aware analysis, it took about somewhat more than half an hour on my notebook in comparison to a few minutes of the SRC matrices. If I compare here all these three levels again, we can see that we of course here have a very, very good, the results seem to be quite close, but we also see that this especially difference here when we use this power-aware analysis. So as a conclusion, or in summary, both workflows complement each other. Here in this table, I got I've shown you a slide overview of both of those both workflows. So in principle, the SRC matrices are suitable for quickly checking the signal characteristics and can be simultaneous capture a large number of signals. Where this EM-aware analysis then takes into account more in-depth real-world PCB effects. So, and that's of course resulting in more intensive simulation time. So it depends on your task what to see of one fast, quick to your results to your PCB, or leave a little bit more, go into more details. Once you have did this first order or second order assessment of your PCB, you may also be interested to see how your power ground noise, if there are any power ground noise issues also available, can be seen here on your design. And this can be done now with this power ground noise analysis workflow. So the main purpose of this workflow is to simulate and to characterize the dynamic noise. That means the voltage fluctuations on the PDN. That means how the power and the ground planes behave under real switching currents, how decoupling capacitors work, and how the plane geometry influence the noise. So it also models the plane and via and decoupling capacitors or structures in your design. Good. That is the setup is similar to the previous, the power-aware setup, and therefore I want to skip to go into more details here. However, as a result, we can see here that is the voltage ringing of the power distribution network without decoupling capacitors, and this is the ringing with enabled capacitors, and you see directly how much these capacitors work and if you still say, okay, there's still a lot of ringing or too much ringing here, you may achieve go into the design afterwards and may optimize some of your decoupling of the capacitor, placing or changing some values. We can also do not only see this transient analysis, we can also see in the 3D representation how this voltage goes through your complete, how the voltage noise is distributed inside your design. And you can see here, without having these decoupling capacitors enabled, you can see that especially in this area we have a big ringing. This means a big noise here. And once you have placed here or enabled the decaps, you can see, oh, it is much more quiet. And that helps, of course, also to see, or maybe afterwards to see where you may also have to add some more decoupling capacitors to achieve a very smooth and noise-free power distribution network. And this 3D visibility enables you to get to understand where you maybe have to place some more decaps to achieve this result. So now let's switch over to some very interesting effects here, like EMI analysis that can also be done here with this tool. The setup is also quite similar to the previous ones, but now we can also achieve or calculate radiation emissions with this workflow. In this case, I've selected these nets here on the left-hand side. You can see here that as the net measure that where I have enabled these nets here. And to do this analysis, we also have to now we have to also make a transient analysis that enables us to bring the complete design into motion. That means, in this case, once we have this transient analysis, we can see how these signals, the power and other signal trace effects may cause any radiation effects. Also, maybe also these effects like routing such signal traces over the splits. Yeah, here's just an image, just a short overview to the designs that also have to achieve here. And now we also want to show you these results. As you can see here now, that is the transient analysis of those selected signals. And here at the top side here, we have the voltage swinging of our PDN, which is also using this non-ideal PDN. So that is similar to the EM array result, but from this we can compute the radiation. In this case, on the left side here, this far field radiation has been computed, and here the green levels show the FCC class A and class B levels. So as a result, as a conclusion, we can see if we still meet those specifications for here, in this case, the FCC specification. You can also see how this radiation is on different, in the vertical or horizontal way by selecting different angles here. You can see it. You can switch here between different angles. That means you can see really the radiation horizontal, vertical direction, or in such other different angles. So in principle, you can move through a complete 3D room. And finally, we can also show, or the near field is also calculated. As you can see here, where we have our selected signals, and of course, as expected, here we have the most radiation in this case. And from this information, you can go back to say, okay, do my system still meet the requirements? Or it also can be that you find here some hotspots here in the near field transition, or in the near field radiation result, so that you can maybe also improve your signal here, signal routing here, to minimize such EMSI effects. So I think it is very, very interesting and useful way to visualize such effects. So now we not come to the end, but just 2 words about the so-called ESD simulation. So in this case, we inject into our design an electrostatic discharge pulse, which is modeled here by like a SPICE model ESD gun, you can say in this case. So these 2 different approaches can be used both to achieve an ESD pulse, or like it is defined here with the IEC standard. So if you do this, if you inject here in the design this ESD pulse, you can see how the current and voltage is distributed through your design. That also includes here some ESD protection diodes, or capacitors, or let's say how this is distributed through your ESD protection schematics. And at the end, you can see if there is still, if there's this high current is damped enough. This is an example that comes as a result. And if you change some values of these ESD protection diodes or capacitors and so on, you can also, you may be available, maybe it might be possible to change here the values and to see the improvements of the complete ESD protection in this case. Well, I think could be also very helpful to avoid damage of your PCBs in real world when you go into your lab measurements. And finally, that's also a very nice way to quickly check your design if specific impedances meet your requirements and if all those, if there are any disturbances, impedance mismatches in your traces. In this case, for example, this sample shows some impedance measurement traces here on a PCB, and we can see here in this case here we have the layer transition from top to bottom. The real the back on the bottom side we have the same transmission line going back, and then you can see okay. On one hand side, we can see okay here we have we meet the desired impedance. Well, we wanted to achieve 100 ohms, but here is in the range of somewhat in the range of 95. So maybe it's in the range of plus minus 10% of our goal, impedance goal. But we also can see that we have here this, impedance mismatch caused by the rear transition from top to bottom. And it might be possible to optimize the via structure to improve the impedance profile. That is especially necessary when you run very high data rate signals like PCI Gen 4 and 5 and so on. That must be very, very smooth. You have to make sure that you have a very, very smooth impedance profile on these traces here. So also, this is the setup is quite simple because you just have to assign here the ports here for the transition where you drive in your TDR pulse, and then on the back side you may also set some ports to calculate the transmission. The blue line here represents the transmission of the signal, that is of the TDR signal. So you can also see from this how much the attenuation of your traces can be analyzed. So that was a brief overview also to the speed EM analysis capabilities. Now finally, I just want to jump over to the Topology Explorer, which is a very, very powerful tool also included into this tool license model. In Aurora, I didn't show to you at the beginning, we have this topology extraction workflow that enables you that you can directly extract traces outside from your board file or even from the constraint manager. And then it will be shown here in this Topology Explorer. You can you can also include not only the transmission lines, but you can also directly compute the real transmission lines based on your layer stackup. So that is one point that you can run, and then you can add some IBIS drivers and receivers to run transient analysis, as you can see here below. This topology extraction workflows also enables you to visualize in a 3D plot your routed traces. And once you want to perform some pre-layout studies, you can change here some these transmission lines by generic W, or the lossy transmission line models that can be created or defined by this transmission line editor. And this transmission line editor is also very, very powerful tool because it represents, you can use the layer stack-up structure and all those stack-up parameters of your PCB, that means laminate, direct electric losses, dielectric constant, edge factor, copper roughness, and so all these parameters go into the calculation of your so-called W transmission line model. So this can be also very, very helpful to do such analysis in a very early layout stage. What you also can do is we have some predefined topologies on here that maybe also represent, that can analyze, for example, crosstalk effects here, where you can see here we have different ways of attaching here the interconnect models. This can be done by different extraction technologies, as I will show you a little bit later on. So the Topology Explorer also can be used for constraining purposes. Maybe you also know from the Signal Explorer that has been used before, the 6XP, where you can define all those electrical C-sets. This can be done also here with the Topology Explorer. We have the same C-sets configuration here on the Topology Explorer as we had it in the 6XP. Then you can write out the electrical C-set, load it into the constraint manager, or even by pressing this button here on the top, you can also back annotate the parameters, the electrical C-sets directly in your constraint manager. So that is also very, very helpful for designing your board. So as mentioned before, we have different ways here to create such interconnect models. We can place here, this is here, different types of interconnect. In this case here, I use this W element for this traceline model, and which has been defined here with this trace editor. But we can also use change here to some extraction engines. In this case, I've enabled Speed EM. If you have further you need much more accurate models like S-parameter models. You may also choose here Power SI for extracting S-parameter models, or high-end, high-frequency models, S-parameter models using the Clarity 3D EM solver. This can be checked out here over this extraction engine. But now, since we have two tokens here on hand, we are limited to the Speed EM extraction. And we can place here this layout block or this FDDT block. Both now extract the layout of your design as we have seen it at the beginning of the EM, of the Speed EM, where you just select here the nets of interest, and then based on the extraction level, those transmission line models are now extracted and automatically put here with a circuit element that directly connects here to your topology. And I think that makes it very, very simple and nice to work only from the layout, from the Topology Explorer, to include all those different layout extraction effects. So once you have configured here your design, just one word here about the big purple lines here. These represent multi lines. Here we have a single line. As you can see, this is only one single line. And once you put more single lines into as a bundle, then you can put them here together to make it more visible for those to connect all these transmission lines to your complete design. So it's also a very, very nice way to connect different blocks, different objects to create a complete channel analysis, for example. Once this is done, you also can configure different your drivers and receiver sides here on your Topology Explorer. It means stimulus pattern, number of bits to be transmitted, data rate, and so on. And then finally you get those transient analysis. So it's, from my side, a very, very powerful tool that can be used at very, very different stages of your design process. So that was, in principle, the fast overview of the complete simulation tools that I wanted to show you that you can enable with these with two tokens. I think it is a very, very wide range of analysis tools. Starting here, maybe also with the InDesign analysis, and that gives you a very, very fast and easy way to improve your layout based on some signal integrity, power integrity, thermal issues that can be found very, very early in the design process and can be changed directly afterwards here in your PCB environment, your PCB design environment. Further deeper analysis can be done here now with the Speed EM tool, which enables you deep inside to dive deep inside to very, very special special effects mainly based on non-linear and non-linear effects of your power distribution network, and maybe also get very fast results by using the SRC matrices to check out if crosstalk effects still meet your requirements, or to see what happens if you have non-linear power distribution networks that also include all those decoupling capacitors on your design. So as a conclusion, you have a lot of tools now on hand to make sure at different design stages that you meet your requirements, that you do not fail any EMC issues, or to reduce, let's say in this way, to reduce the possibility of failing your tests or whatever else. You can do a lot of things very early, like what if analysis, what happens if I do this and that, before going into the production of your PCBs, so that avoids a lot of money probably, and also reduces the time until you bring your products on the market. So that was my final words, and now I would like to switch over to Petra.
Thank you very much, Dirk. So let's get straight to the questions I have here. Can you please tell us something about hardware that is recommended for simulations, please?
Oh, yeah, the more the better now. I did all these analysis with my notebook. This is not an office notebook, but it's more like a workstation that can be used also for your layout tools. So you do not need a high-end workstation or server that might be used for a 3D EM analysis. So typically, such a CAD workstation should be quite enough.
Can you tell us about Sigrity X token license? What kind of model is this? Is it a network license or floating license or whatever?
From my knowledge, we do not have any user-specific licenses or node lock licenses. So these token models are always floating licenses. That makes sense because this is not assigned to one user. So everyone can use it when he wants to use it. So you do need a floating license.
Good, thank you. Can you briefly explain us when which license is checked out? Can you tell us more about that?
I think you mean when the license is blocked. I assume that is something. It goes in this direction. So let's say it in this way. If you start speed EM, then the two licenses are blocked. You can do the simulation or analysis as long as you want, and at this time the license is blocked. The same effect is the same when you open the Sigrity Aurora PCB editor. This also requires two licenses, two tokens. But if you work on your typical PCB design editors like OrCAD X Professional or Allegro X, none of those licenses will be used as long as you do not start the analysis. That means as many, depending on the licenses you have for your PCB designers, PCB design editors, you do not check out any of these tokens. It's just in this case, in this moment when you run the simulation, it is blocked. So since this, I would say, since the analysis mostly for only a few minutes, then your colleague maybe have to wait a few minutes until he also wants to simulate something. But I think that should not be a breaking point to use these licenses. So in principle, you can run as many PCB editors in parallel as you want, and just in that moment you run the simulation, it is blocked, and it is free again when the simulation is done. I hope this answers the question.
Absolutely, thank you. Are these simulation tools specially designed for Cadence board files, or is there more possibility?
I have to say it with a clear yes and no. that means yes. Since the InDesign analysis can be done only with the Cadence PCB editor, so this is related. The InDesign analysis is related only to these board files, Cadence board files. But SpeedEM has an open ECAD data import filter, so that you can use many other ECAD tools like IPC 2581, ODB++, and some other native third-party vendors. So that is also specially designed to be open for third-party vendor data.
Right. And the final question, is there a way to test the presented tools?
Very good question. Let's speak over to the next slide. I just forgot to switch over to this side. If you want to test, we have some workshops available where we have pre-configured simulation servers where you can test these software tools. This can be done on your own, but I give an introduction, especially into the InDesign analysis, starting with impedance and coupling scan, and next session is also covers all these power integrity tools. Once this is not enough, or you want to test them the software on your own design, you are welcome to send us a request, and we can send out a test license to you upon request, and we also will help you to start with the first analysis as we do it here with these workshops.
Great offer. Thank you very much. So I think we're at the end. Thank you all for your interest. Thank you all for your time. Have a great day and see you next time.